Hello and welcome to this video for CE 108 Mechanics of Deformable Solids. So now that we have seen in the previous chapters the concept of stress and of strain and the Hooke's law to convert stress into strain or strain into stress, now in the following chapter what we are going to see is different examples of different types of deformation under different types of loads. And the general approach will be pretty similar in all those chapters, in the sense that we will always follow the same general organization, in the sense that we will start from what we know, that is to say the external loads that are applied to a given structure. So that's what we typically know. So this is the information that is known. Then based on this, you will be able to calculate the internal loads acting within the structure. Based on the internal loads, you will be able to calculate the stress, both the shear stress or the normal stress, depending on the types of loads that you have. And then based on the stress, then we will be able to calculate the deformation. Either in terms of strain or in terms of absolute elongation or other types of potential deformations. So we are going to see this relationship on how do you go from the external loads that are applied to the ultimate deformation of the material. And for this, we are going to consider different cases. The case of axial load, this is what we are going to see today. And then after that, we will see the case of the deformation that is induced due to torsion. And then we're going to see the case of bending and shear deformation. So in this class, in CE 108, we are going to see four main types of deformation. So we're going to start by briefly talking about those four types of deformation. So the first type of deformation, and that's the one that we are going to talk about this week, is the case of the elongation that is due to an axial load. So when you have an axial load deformation, that is to say, if you have a beam like this and then you have an axial load that is along the longitudinal axis of the beam, then the outcome of this will be that the beam can be potentially elongated or can potentially shrink. So in this case, you will have the cause that will be causing the deformation will be, in this case, the axial load that are applied. This is going to be the cause of the deformation, and then the consequence of this deformation is going to be the elongation of the beam. The elongation itself of the beam will be the consequence. So what we are going to see is how to relate the cause to the consequence. We are going to see that in the case of the axial load for this week, but we are also going to see in the following week some other types of deformation. For example, the case of torsion. So in the case of torsion, in this case, so if you have a beam like this, which typically would be some kind of shaft, then what we are going to see is what is the type of deformation that is due to the application of a couple. So if you have a couple like this that is applied, that is causing a twist deformation of the beam. So in this case, the cause of the deformation would be the application of a couple, so a moment that is along the longitudinal axis of the beam, and the consequence of this will be the twisting. You will have a twist deformation, so you will have a twist angle. The beam is going to undergo some torsion, so the consequence will be the twisting of this beam. Then the next type of deformation that we will see is the case of a bending. So for example, if you have a beam like this and you apply a moment like this, then in this case the beam is going to be deformed like this. We'll have a smiley face. In this case, the cause of the deformation will be the application of a bending moment that is going to cause the beam to be deformed, and the deformation in this case will be a deflection of the beam. The beam is going to be deflected. And the last case that we're going to see, which is related to the case of bending, it's the case of shearing, where in this case, if you have a beam like this, and you apply, for example, 3 transversal force like this is also going to be causing a deflection of the beam. In this case, the cause will be a shear force, a transversal force along the transversal direction of the beam. And this shear force is also going to cause a deflection of the beam, just like the application of the bending moment. And so in each case, we will want to see for each of those deformations how to go from what we know, which is the external loads that are applied or the external moments, and how can we use this information to predict the deformation of the body. So first what we're going to see is if you know for a given beam what are the external loads that are applied, the external axial loads, how do you get the internal load, which is going to be always the first step in solving an axial load problem. We need to calculate the internal load within the beam. And once we know the internal load, then we can calculate the stress. So for this, let's consider a general case where you have a beam like this, for example. Let's assume that you have a fish like this. And so this beam is attached to a fixed support on the left at x equals 0, and then the beam has a length L along the x-axis. And let's consider that this beam will be subjected to a series of arbitrary external loads. So you can have a load P1 here, maybe potentially a load P2, and then let's say, for example, another load P3, which might be pointing in the other direction like this. So in this case, typically what we will want to do in this case is to determine where is the maximum risk of fracture. So we want to know for which x, at which position x, the material is the most likely to break. And for this, if we want to determine the maximum risk of fracture, what we need is to calculate the stress. We know that if the material is going to break, it is because the stress at a given point of the material will exceed the ultimate stress of the material. So we need to calculate the stress as a function of x. And then we need to look at which point x is the stress maximum. So for this, if we want to calculate the stress, so we will need to first calculate the internal load as a function of x. And to calculate the internal load, here there is nothing new. We will need to use the method of section. So the method of section is still going to be the method that we will be using to calculate the internal load. So if we want to calculate the stress as a function of x, so we need to calculate the load for any arbitrary x. And the way we are going to do this is to select a given x that is between 0 and L. So we fix a given arbitrary x. And then, so we're going to use the method of section. That is to say, we're going to cut the fish into 2 parts at the position x. We define this fictitious section at the position x. And then, so we will use the method of section. So we can cut the fish in 2 parts and either isolate the head of the fish like this. In this case, we would be isolating the fish between 0 and x, or we can also isolate the right part. So we can isolate the tail of the fish like this. In this case, we would isolate the part of the fish between x and L. And in this case, whether we isolate the left or the right doesn't matter. We will need to now use the method of section and say that since the entire fish is at equilibrium, each part of the fish also has to be at equilibrium, so that we can either isolate the left or the right and write the condition of equilibrium and find the value of the internal load, where the internal load comes from the fact that if you have isolate the left part of the fish, for example, then the right part acts as a fixed support for the left part. So you have a load that is going to be transmitted from the right to the left, and you will also have a load to be transmitted from the left to the right. So here we need to start to have some convention on what we are going to define as being a positive internal load. We need to define a sign convention of what we are going to call an internal load that is positive. And here the sign convention that we will be using is that the internal load, we are always going to define it as pointing towards the outside. So that's something to remember, that the internal load, the sign convention for the internal load is that it's always pointing towards the outside. So if you define the internal load on the right surface like this, on the surface that is applied on the right part of the material, then the load will be pointing towards the right. And if you have a left surface here, then the load will be pointing towards the left, always towards the outside of the material, always pointing towards the outside. So keep in mind that this doesn't tell us anything about the sign of the projection of this internal load. Like if we take this load here on the right surface, it's going to be pointing towards the positive x, so it's going to have a positive projection. And on the other hand, if we take this, if we decide to isolate the right part, then the internal load will be pointing towards the left, and then it's going to have a negative projection because it's pointing towards the negative x. So it's important to notice that in this case, the sign of the internal load is going to be positive if the internal load is pointing towards the outside. That's the positive convention for the internal load. But the projection of the load will depend on whether we isolate the left and the right. But at the end, we need to do this. Why? Because we need to have this consistent definition for the load. We know that the load is the load, the internal load is the load applied by the left to the right or the right to the left. We know that due to the principle of action-reaction, the load applied by the left to the right is going to be the same as the load applied by the left to the right. It's going to be the same as the load applied by the right to the left, but with an opposite sign. That's the principle of action-reaction. So if we want to remain consistent in our definition of the internal load so that it doesn't depend on whether we isolate the left or the right, then we need to always define it as pointing towards the outside. So we are not going to define the load as always pointing towards the right, for example. We are going to define the load as always pointing towards the outside. So we'll come back to this, but it's important again that whether you isolate the left or the right, the internal load always points towards the outside. So based on this, so we will define the internal load as the load, the normal load that is applied from the right to the left or vice versa. So that's going to be at a given position x, the normal load that is applied by the right section on the left section, or vice versa. So this doesn't matter. You can isolate either the right or the left. This will not affect the value of the internal load. Then, so again, regarding the sign convention, we will always define the load as always pointing towards the outside. So this is what we are going to call, so the load, we are going to call it P. The load will depend on the position X, and we are always going to define it as pointing towards the outside. So if you cut a material into parts and then you create two new surfaces, you will always define the load as pointing towards the outside of the material. So what it means is that if you have a case of tension, so a case where the material is subjected to a tensile force, then you will have a positive internal load. So in this case, if you cut the system like this, then necessarily that will result in a positive internal load, and this positive internal load will induce an elongation of the material. And on the other hand, if you have a state of compression, that is to say a material that is subjected to some compressive force, then the internal load will be negative, and then you will have a case of shrinkage, where the size of the beam, the length of the beam is going to decrease. So let's discuss a little bit more about why it's important to always define the internal load as pointing towards the outside of the member. So for this, let's consider a simple beam like this that is subjected to simply an external load that we are going to write P naught. And then, so in this case, same thing. If we want to calculate the internal load at a given position, we are going to select an arbitrary position X at a given position within the beam. And then we can decide to either isolate the left or isolate the right. So this doesn't matter. We should get the same result whether we isolate the left or the right. So let's assume that first we are going to isolate the left, and then we are going to see the case where we isolate the right section of the beam, and we will make sure that we get the same result. So if we isolate the left, so let's assume that we have a beam that goes between 0 and L like this. So if we isolate the beam, then we will get the part that we will be isolating will be the part of the beam between 0 and the point X at which we decided to cut the beam. So now, what are the external loads? So we have the load P naught applied at X equals 0. And then at X equal L, so you will have the load that is applied from the right part of the beam to the left part. And in this case, we are going to, so this is the internal load. This is what we are looking for. And we will define, we'll use the positive sign convention. So we will be defining the internal load as pointing towards the outside. That is to say, pointing towards the right. Now, if we isolate the left, so same thing. So now we have the left part of the beam. This is what we will isolate. It goes between X and L. We still have the load P naught applied on the right. And now on the left, we have the load that is applied by the left to the right. Again, now we will define this the same internal load, and we will again use the positive sign convention. So we will now define this load as pointing towards the left. Why? Again, because we always want to define it as pointing towards the outside of the material. So now let's make sure and let's check why we sometimes define this load as pointing towards the right, and now defining why we're defining it as pointing towards the left. Let's make sure that those two definitions are actually consistent and will give us the same value of the internal load at the end. So for this, we can write the equation of equilibrium for both cases. So we are going to say that the sum of the projection of the force along X equals 0. So in this case, if we look at the first case where we isolate the left, so first we have the load P naught. That's the load that is applied on the right, on the left. Sorry, it has a positive. It has a negative projection. It's pointing towards the negative X. So its projection is minus P naught. And then so we have the internal load. In this case, again remember that irrespectively of the sign of the internal load, whether it's a positive or a negative internal load, its projection may be positive or negative. The projection of the internal load has nothing to do with the sign of the internal load. An internal load that is positive means that the beam is under tension. An internal load that is negative means that the beam is under compression. So this is about the sign of the internal load. Now, when we're talking about the projection, the sign of the projection is positive if the internal load is pointing towards the right. The projection of the internal load is negative if the force is pointing towards the left. So the sign of the internal load has nothing to do with the sign of the projection. In this case, the internal load is pointing towards the right, so it has a positive projection. So in this case, we find that those two forces must be balanced. So we find that the internal load is equal to P naught. We find that in this case, if P naught is positive, then the internal load is also positive, which is consistent with the fact that this beam is under tension. So now let's look at the case of when we isolate the right part. So we have the force P naught that is applied on the right. This time P naught has a positive projection because it's pointing towards the positive X. And now in this case, even though this is the same internal load, now the internal load is pointing towards the left, which means that now it has a negative projection. No, those two forces must be balanced. So in this case, you find that again, the internal load is equal to plus P naught. So here, this example is here to show you that if we don't define the internal load as always pointing towards the outside, then we won't have a consistent value for the internal load, whether we isolate the left or the right. Here, this is because we always define the internal load as pointing towards the outside, that we are able at the end to find the same result for the internal load, which in this case is positive, means that the beam is under tension. Irrespectively of whether we isolate the left or the right, we find the same result. And this is because we always define the internal load as pointing towards the outside. We find that in certain cases, the internal load will have a positive projection. In other cases, the internal load will have a negative projection. So this can change depending on whether you isolate the left or the right. The projection of the internal load can change, but the internal load should always be defined as pointing towards the outside to remain consistent. So now that we have the internal load, we can directly use this internal load to calculate the normal stress, where in this case, the normal stress in the case of an axial load problem, this is what we saw in the chapter on stress, the normal stress is simply going to be the load divided by the area. So the stress will depend on each position x, and in this case, the stress is going to be defined as the ratio between the internal load that we just defined at this position x, divided by the area of the cross-section. Remember that the area of the cross-section can also depend on x. For example, if you take the case of the fish, the fish has a cross-section that depends on x, where in this case, as a function of the position x that you have, the area of the cross-section will not be the same. So you have to keep in mind that both the load and the area can both depend on x. And in this case, because of the way we defined the sign of the internal load, we can directly use this formula, because the sign of the stress will be the same as the sign of the internal load. So if we define properly the sign of the internal load, then this formula will also properly define the stress, the sign of the stress, in the sense that if you have a case of an elongation, then you will have both a positive internal load and a positive stress. And if you are in the case of a compression like this, then both the internal load and the stress will be negative. So the sign convention of both the internal load and the internal stress are both consistent, so they are both related with this formula. So typically, the kind of things that can be asked for you in problems would be to calculate the value of the stress at any position x to determine at which point the stress is maximum, to determine what is the point at which you have the maximum risk of fracture. And one graphical way to do this is to rely on diagrams. So the kind of diagram that you may be asked to plot would be the load diagram, where the load diagram would be a plot where you are plotting the value of the load, the internal load, as a function of x. And on the other hand, you will have also potentially the stress diagram, where in this case, you would be plotting the value of the stress as a function of x. So by plotting the evolution of the load and the evolution of the stress as a function of x, then it makes it easy to graphically determine at which point the stress, at which point x, the stress is going to be maximum. So now what we are going to see in the next section is, once you have the load and once you have the stress, how do you determine the elongation of the beam?